Hi everyone. In this new module, we are going to look into the different algorithmic paradigms as well as the different design techniques for creating new algorithms. We'll specifically look into two different design paradigms. The first one is greedy algorithms and then dynamic programming. We have already covered a lot of different data structures throughout the course, and implicitly you already learned about the different algorithms that were associated with these data structures. We'll try to situate whatever we learned into these different algorithmic paradigms, and then we'll learn some new algorithms that will allow you to compare and contrast what are the different paradigms and what are the key differences between the affordances that are offered by these paradigms. So without further ado, let's get started with algorithmic paradigms, which is they are roughly four big categories of paradigms that we cover in this course. There are many more that are outside of these. If you take any graduate level algorithms course, they might also cover the reduction paradigm. They might cover divide and contrast and so on. But we will be covering just four of those, which is the first one is brute force, the second one is divide and conquer, then greedy algorithms and dynamic programming. So when we talk specifically about brute force, you have already seen a few algorithms, which is brute force is the most naive way to solve a particular problem, where you look at all possible solutions to a particular problem and then pick the best one, which is it will always give you the correct answer, but it can be computationally much more expensive, which is we saw selection sort, bubble sort, insertion sort, and different NP complete problems. If you do not know what this term is, in the next module you'll understand what are NP complete problems. We also looked into the divide and conquer paradigm, which includes breaking a problem into smaller chunks and then trying to solve it, which is we saw algorithms like binary search, merge sort, and quick sort that kind of fall under this paradigm. Then we have these two new paradigms. One of them is greedy algorithms. You have already seen a bunch of algorithms like when we covered graphs, which is minimum spanning tree, Kruskal's prims, or Dijkstra's and Bellman-Ford all fall under this paradigm of greedy algorithms. Dynamic programming is another type of problem solving technique where you divide the problem into smaller chunks and you see repeated patterns in those smaller chunks and try to pre-compute the results of those smaller chunks which you have already solved and use them to solve the larger problem. So essentially a few properties of these paradigms, like let's say if we talk about brute force, a few properties are that we generate and test a set of all possible combinations, and then we return the correct solution. So it will always guarantee you a correct solution, but it might be really expensive. A few other examples would be let's say if you were trying to find duplicates and we were trying to see all possible solutions, that's an example again of brute force. Or if we are trying to find the divisors of a number, and if we check every number from 1 to n or square root of n or n divided by 2, we run a loop and try to see if n mod I, where I is running from 1 to n or square root of n or n divided by 2 depending on your algorithm, you are checking all possible solutions. The second paradigm that which is the divide and conquer paradigm, it breaks the problem into subcomponents, which is typically done using recursion, which is it's easier to represent these problems using recursion. And we saw already quick sort, merge sort, binary search, or the 1D peak finding algorithm. If you remember what we covered in the first week, all of those actually fall under this category of divide and conquer, which is we divide the problem into smaller chunks. We solve the basic component and then we combine the solutions to these sub-problems to generate a larger solution. The next one is dynamic programming, which is a programming design technique or an algorithm design technique where every problem follows these two properties. The properties are optimal substructure and overlapping subproblem. So what is optimal substructure? Which is a solution to a large problem that can be obtained by solution to smaller optimal problems, which is like all the problems that we are going to solve using dynamic programming should satisfy these two properties, which is, let's say if we have a problem where you are trying to find the sum of elements in an array, and what you have done is you have broken down the array into smaller chunks, and if you have like 1 2 and 2 3 3 4 as the next numbers in the array, if you sum these numbers up, and if the total sum can be actually more than the sum of these two elements, or if you if the global solution to a particular problem is not cannot be computed, or is not the actual global optimal solution, by solving the sub problems, then you cannot apply dynamic programming to that particular problem. The second property that it should satisfy is overlapping sub problems, which means the same problem must be repeating again and again. And what we can do is we can solve the solutions to these smaller sub problems, and then we can store these results, and as we are seeing these problems again and again, we can just use the pre-computed solution, which is they are again like two different variants of dynamic programming. One is top down and the other one is bottom up, also called tabulation and memoization. We'll discuss this when we start covering like other algorithms, when we start covering dynamic programming algorithms. Now, dynamic programming always guarantees you an optimal solution in terms of correctness and time, which is these are usually fast to compute compared to the other paradigms like divide and conquer or greedy. Also, they will always give you the correct answer. That is a key thing. Now, one thing to note here is how do these two paradigms differentiate, which is divide and conquer and dynamic, because essentially we are again breaking down the problem into smaller components. But the key difference between these two paradigms is the divide and conquer paradigm, essentially you will not see overlapping sub-problems. You are just breaking down the problem into sub-problems, but they might not be overlapping. So I'll give you a very small example, which is like, let's say if we are trying to find a Fibonacci sequence of like f of 5, we know that this is essentially equal to f of 4 plus f of 3. And then when we do f of 4, which is Fibonacci of 4, that is essentially equal to f of 3 plus f of 2. So here we see like these sub problems are essentially overlapping, which is they are coming again and again, okay, when we are trying to solve the problem. But when we specifically talk about divide and conquer, that's not the case, which is like when we try to divide the problem, like let's say it's quick sort or merge sort, what we did was we divided the array into two halves, but these two halves might be the same, but most of the times they are not the same at all, which is they will be completely different, and you'll not see the same sub problem occurring again and again. So that is one of the key differences. The last paradigm is the greedy algorithm paradigm, and in this paradigm you basically solve a particular problem by using some sort of a heuristic. And what is a heuristic? It's basically an idea that you take to maximize an objective function. What those are, we are going to discuss very shortly. So essentially you use a heuristic, like I can give you another example of a heuristic, which is like, let's say if you want to go into a school, okay, like you want to take admission into another school, what you might do is you might get the opinion of those who are close to you. You might not be going to the entire like every person in the world and ask their opinion, but you might just use your heuristic that this person is like pretty knowledgeable, like somehow you know that, and you might just use those cues to determine which school you should take admission into. But it might not be the case that that's the best school that you can get into, like that is just based on some reliable sources or based on some heuristic decisions that you made, which is you might be taking into account only opinion of those who you like rely on or trust. It might give you the good solution but not the best solution. So greedy algorithms essentially do not guarantee something called a globally optimal solution, which is they'll give you a good enough solution, but not the best solution. When we cover dynamic programming, we'll see a few examples like Fibonacci sequence, assembly scheduling, knapsack problem, and bin packing. And when we cover greedy algorithms, you'll also see like Huffman trees, bin packing, knapsack, like so you kind of get a contrast on what are the key differences and how those solutions look like. In the next video, we'll get started with the optimization problems. I'm going to describe to you some of this terminology, and then we'll look into more greedy algorithms. Thank you.